Okay, here we are. Here's Shout and Flange are about to make a Webbock. Is that the official name?
Yes.
It's going to be stringed between these trees. Here's some of our tools, the ladder, of course. Shout. The rope. This is 2,000-pound test rope, okay? Should hold up anybody, and that should be enough, but Charles is going to check on that. We got our drill, extension cord, got some of these hooks to weave them through, and this is for like driving the things in. Okay? Okay, so the first step, Charlotte, is you got to untangle all this, but before that, figure out your number of diagonals that are in a heptagon. We got a heptagon going here. And do we have enough rope to cover all those diagonals? Now, not all the diagonals are going to be the same length, but if you get your typical diagonal, okay? Charlotte's going to get on that, and I'm going to get on putting in the things. No, there's not 7 diagonals, there's 7 sides. Do we have enough rope to do all this? She doesn't know. She's going to find out. Okay, here comes the O-Man to help out. Here's the question. I'm going to present it to both of you. Figure it out. Do we have enough rope here to make the Webbock?
How much rope do we have?
Well, that's one thing you find out. And then how much rope do we need? Okay? I'm going to proceed with my part, that is getting the hooks in. Because if we don't have enough rope, I'll go out to get some more. Okay? But first of all, you know your old formula for the number of diagonals in a regular polygon.
Yeah.
You get that number, and then you figure out your typical diagonal, and multiply by that to see about how much rope we need.
I never made a formula to figure out the length of all the lines.
That's why you use your statistical analysis. Could you use like the average length, or do you actually want to multiply each of the short diagonals by whatnot?
Why don't we just start weaving it if we don't have enough rope? We'll go get more rope.
Also, as a polynomial, as a polygon gets more sides, or a regular polygon, we expect the difference in density of the diagonals between very high density near the edges and low density in the middle to become more extreme.
Okay.
Right? So how big is this polygon?
Show everybody the number of trees here. 1, 2, 3, 4, 5, 6, 7. Notice how it's not regular. In fact, it's somewhat convex right there.
Yeah. So
that's going to be an issue.
You're not even going to want to do this diagonal between these two.
Oh yeah, for support. Oh yeah. That'll be critical.
And the formula wouldn't work because it's so irregular.
Okay, just an estimate to see if we got enough rope, okay? I'm going to stop the tape now. We're going to have some answers soon, okay? While I'm getting the hooks in, you guys can figure this out, all right? Go! Now it's going. Explain that again, Owen.
Okay, the Dreamweaver plan, which I have, is this. You start by doing all the shortest, what would you call them, non-diagonals?
Yeah, the sides.
The sides.
The sides,
yes, the exterior.
Mm-hmm.
Then, instead of doing the interior diagonals, you go between the midpoints of adjacent sides.
Okay? Really?
So you get a smaller polygon with the same number of sides on the inside, and you repeat this process going into the middle. And that way you'll actually get a higher density in the middle, which is what you want.
Don't you normally get a higher density in the middle from...
No, you'd have a hole in the middle.
No, not a huge hole. Come on, the diagonals going this way, no, there won't be a hole in the middle.
There'd be a hole about this large in the middle.
Here's the problem with that though, Owen, don't you have an
infinite?
Well, are you trying to tie it to the midpoint? And that's a pain.
No.
Making all those knots.
No.
No, you're not tying to the midpoint, it's just going to stay there from tension?
You actually pull the sides inward a little bit, which is fine. You want that. Gives it class and taste.
What do you think, Charlotte?
I have no idea what he's talking about.
He's talking about heptagons inside heptagons inside heptagons.
Yeah, I've done that.
Once we go around the outside, then you kind of go around the midpoints and the midpoints again and weave in that way.
So it's like we do all of the diagonals, and then in the inner heptagon we do that again. Is that what you're saying?
No, he's not saying all the diagonals first. He's just saying you make the heptagon, and now you take the midpoints of all the sides of the heptagon and then connect those.
Form another heptagon.
But then you're just going to put like, are you going to tie it at all? It's going to keep sliding. If you don't tie it, it's going to slide. You're okay with it sliding?
You have to tie it, yes.
Okay. Maybe, I think we might have room to do both people. Because that sounds like a more comfortable surface to sit on. But the other thing sounds more stable. So we start with the diagonals thing, and then above that is this weaving thing. What'd you call it, a Bessier curve?
Dreamcatcher.
It's
Dreamcatcher.
It's related to a way that you might compute a Bezier curve,
Oh, okay.
but Dreamcatcher. That's the word I would use for it. Dreamcatcher.
All right. So we have a plan. Diagonals at the base, and then a Bezier curve for the top, because I think the rope will handle both.
Okay, the perimeter is 33 feet.
33 feet.
Yeah, probably take away from that. And since they're basically going to be the outer level, the skipping one level and skipping 2 level, so it's probably going to be a good 100 feet of rope.
Okay, go find out if you got 100 feet of rope. We're going to need that all entangled anyway for better webbing. Okay, and I'm thinking I'm just going to put the hooks in at eye level for my convenience in measuring. The ground looks fairly level. And if it's at eye level, you'll be able to leap in it from this little thing right here. Right?
Yep.
Check. Apparently it helps the workers if you crank up the mica and open up the windows. Char's rocking now. Char, what are you doing? No, that goes through the eyelets, Char.
I am measuring by wrapping it around, and if it
Oh.
makes it 3 times around, then we definitely have enough.
Oh, that's her. She's okay. Measuring without measuring tools. That's amazing. Okay, I've got all the holes drilled, and I've put one of these in just by using this. I started with the maple just to avoid infecting the maple with whatever the aspen have, because sometimes you'll see the maple has these strange dots on it as it gets close to the aspen. So I did clear out a lot of aspen in this area. Charlotte seems to be coming along here. I've lost one of my workers. She looks like she almost made 3 laps with this. Oh, what's the report, Charlotte?
Miscalculation.
Oh no.
Okay, so in a regular heptagon,
Yeah.
the length from just 1 to 1,
Yes.
like one side to the
Yes,
next
one
point,
side. Yeah.
compared to 1.2 point that skips 1,
Yeah.
compared to 1.2
Like all the way
skipping
across,
2,
just about.
is
Yeah.
1 to 2 to 3. So
Really?
we need to do 6 times the average length between them. The average length between them is 5 feet, a little less.
Okay.
So 5 times 42 is a lot of rope.
So you think it's going to take both our lengths?
Probably.
Okay. And you know, we could get by with this maybe not doing the outer ring. How much does that really add?
The outer ring is just 33 feet.
Yeah, okay.
That doesn't actually help excessively.
Well, you know, we also have as a resource is all those belts you earned as a kid. And I thought that might be a nice way to tie some of the rope together at some point, but I don't think those are going to weather so well. This rope would probably weather pretty well.
Right, yeah.
Okay. Well, at least get the rope untangled and get the other one untangled in there. And I'm just about ready because I've got one of the hooks in and now I've got all the hose drilled.
Okay.
So, okay. Flange. Okay, Charlotte has been doing some research here, as you can tell, with her measuring device and her diagrams. And we've got all the hooks in. 1, 2, 3, 4, 5, 6, 7, and back to here. Now we just have to get a good spot to get the camera so we can tape this whole event. Okay, we're taping. We're starting to run the big rope. And Charlotte's going counterclockwise around. Okay, all right. fun. I can help you feed. Keep pulling. Okay, coming along nicely. We still have a whole other section of rope, so I think we're going to try Owen's idea with the midpoints. Keep cycling in there. Yeah, midpoints on midpoints. So get a good look at this, kids. And here's the question. Here's the question. How many intersections are there inside? You can try and count them, but the Pip Project is to come up with, no matter what the size of the original heptagon, what is the range of possible diagonal intersections you can have. The range of possible diagonal intersections. What's the smallest number of diagonal intersections? What's the largest number? You can count the exact number for a perfect regular heptagon, but what about like this one when it's not a regular heptagon? In fact, it's a convex heptagon right here. That's one of the issues Sharp was talking about. It didn't make an inner heptagon, it made an inner hexagon, because one of these diagonals should have been coming a lot farther over. Okay, that's the Pip Project.